So let's take a look at this video we have right here. We've got a pole right here. And just off side of the screen, we have another pole that's right here. And there's a string attaching these two poles. Now what I have is I have a pendulum. And if you see my mouse, it's right here. Now this one is about the same length as this one. I know they look a little off, but that has to do with camera perspective. I also want you to notice that this pendulum right here is about the same length as this pendulum right here. So what you're going to see in a second is my hand's going to come up and I'm going to move this pendulum right here. So by moving the pendulum like that, I've put energy into it. What you'll notice is I didn't move any of the others. Now you can see there's a little bit of vibration from all of them right now, but they all eventually stop moving, except this one right here. Do you notice how it's starting to get faster and faster? And take a look at this one right here. Notice how it's getting slower and slower. As time goes on, what's going to happen is this is going to stop moving entirely, which it basically has now, and now this is swinging a lot. But as soon as I've said this, what you're going to start to notice is now this is starting to slow down, and this one is starting to speed up. And I'm just going to go ahead, we won't watch the whole thing. We're going to be able to double the speed. Now look, all the energy has went back into pendulum number 1. But just as soon as this one has stopped moving, this one is starting to slow down, and this one is starting to speed up. And what this has to do is it has to do with the concept of resonance. The first pendulum has energy, and it's producing a wave on that string. And it's resonating with the second string because they're the same length. As a result, there can be energy transferred, being bounced back and forth. Now, this is a fun little example, but does this apply to the real world? Well, it does. This was a very famous bridge from the 1940s. And what happened here was the wind was blowing along with these strands right here. And as a result, do you start to see this bridge moving? This is concrete and steel. But what's happened here is the energy from the wind started to sway with the bridge, and the bridge started moving back and forth. Now, although this video is from the 1940s, this still happens in today. There's a bridge out in England, the Millennial Bridge, where it had the exact same problem, which starts to sway as a result of people walking on it. This brings us to today's topic, which is standing waves. Now, what is a standing wave? It's a standing wave pattern is a vibrational pattern created within a material when the vibration frequency of the source causes reflected waves from one end of the medium to interfere with incident waves from the source. What does that actually mean? Let's take a look here at a guitar. If you're taking a guitar here and you're playing it, when you pluck the string, the energy will go all the way down the string and all the way back and all the way down the string and all the way back. And it keeps doing this back and forth. This can occur so that interference patterns occur on the guitar, so we can see a specific pattern. I'll do another example. If we look at the entire length of this guitar, if I put my finger directly here in the center, and this spot right here is halfway between the top of the neck and the bottom of the guitar, what you'll notice is when I do this, you can still hear a sound. Now the reason why it works right here is because I'm producing what's known as a node. If I put my finger a little bit higher or a little bit lower, it doesn't work. But if I put it exactly in the center, we get a sound. Now what does that look like? So if you think of the guitar string, from the neck all the way to the bottom, when you pluck a guitar string, the string will start to go up because the energy transferred one way, and then it bounces back to the beginning. And it'll go there and back and there and back, and it keeps doing this over and over again. Now, if you look at this first half, this would be like considered to be half a wave. So it's half a wave on the top and half a wave on the bottom, making a full wave. Now, if we look back at our guitar, back to our example, where I was putting my finger exactly here in the middle, where I'm here to here is the same distance as here to here, and we can hear a sound. What's happening there? Well, what we're basically doing is we're producing what's known as a node right here. So my finger where it's touching is not allowing energy to go through. But we can still have a wave over here, or a wave on the other side. So in our first example, it was half a wave on the top, half a wave on the bottom. This time, we can see a full wave this way, or a full wave on the other side. Well, what if I was to put my finger right exactly 1/3 of the way up the guitar neck? So like right here. So in other words, the distance from here to here is exactly 1/3, and from here to the bottom is 2/3. Yet again, we're hearing another sound. Well, what's happening there? Well, if we keep trying to picture this, is I'm putting a node right there. I'm not allowing energy to be transferred through there. So a wave is being created here, but the same size wave is being created over here. So in this particular case, we have two nodes. The first node here is where I put my finger, but the second node is created just from the natural frequencies that occur within the string. So, to summarize the terminology, these spots where not a lot of movement is occurring, this is called a node. And these spots where there's a lot of movement, it's the opposite. It's an antinode. So all instruments can be categorized in one of the following three ways. The first one we're going to talk about is when you produce a standing wave on a string. So guitar string, piano string, violin string. The first harmonic is going to look something like this. This is just basically when you pluck the string. It'll go up and down. And it's producing half of a wavelength. We've got two nodes here, one on either end. This is known as the first harmonic. The second harmonic is when we're producing a pattern that looks more like this. So we've got three nodes, one in the middle, two on either end. And you can see we're producing a full wave, so 2 out of 2. If we go to the third harmonic looks something like this. There's 1.5 waves in here, which corresponds to the 1.5 right here. And we have 4 nodes, 2 on the ends, and then 2 here in the middle. So I wrote nth harmonic to just show you what the general formula is. Whatever harmonic you're looking at, n divided by 2 times the wavelength is how long the actual string is. And to figure out the number of nodes, it's whatever harmonic you're on plus 1. So the opposite example is going to be a standing wave in a column with 2 open ends. So any sort of woodwind instrument, flute, you get the idea there. When you're blowing through a flute, for example, this is what sound you're going to hear. This is the first harmonic. Now it's a little bit confusing because it's the exact opposite of what we saw with the string. In this particular case, the node here is in the middle, and we have the wind going down and up. So it's producing that longitudinal wave. But it's still only half a wavelength that's being produced. And we can see there's just one node here in the center. For the second harmonic, we're producing a full wave. So you can see it goes from trough to trough or crest to crest, depending on how you look at it. We have 2 nodes here, one right about here and one here. In the third harmonic, yet again, it's going to be 1.5 wavelengths if you go ahead and count it. And we've got 3 nodes here, here, and here. So the general formula for this is the same as with the guitar, except the number of nodes is just whatever harmonic you're on. So if you're on the 5th harmonic, you're going to see 5 nodes. So our last example here, which is a standing column, where you have one fixed end and one open end. If you want to picture something, picture, for example, wine glasses that have water in them. You can take your finger and rub it around the top to get a sound. Or think about a bottle that has liquid on the inside, and you blow over the top to get a sound. These are 2 examples of what we're talking about. And what happens is when the air is going over top of that, it's producing a node here at the end. And it's producing 1/4 of a wavelength. This is known as the first harmonic. Now, just due to the physics of how this works, there is no second harmonic in this case, but there is a third harmonic. That's when we produce 3/4 of a wavelength. Now you'll see there's 2 nodes, one right here, one right here. And because it's 3/4 of a wavelength, this is the formula we're going to use. Yet again, there's no fourth harmonic. It's just not a thing that exists in this case, but the fifth harmonic does. And we can see yet again there's 3 nodes. And this is the formula we're going to use. So in general, if you want to figure out any harmonic, the formula is L equals 2 times whatever harmonic you're looking at minus 1 divided by 4 times the wavelength.